Okay, let's start the discussion session. Please, really, feel free to ask any embarrassing questions, any of the lecture. It's really the time for you to catch up. Don't be shy.
Since nobody is asking question, may I ask question? So I have a question to Nima. So toward the end of your lecture today, you was discussing relation of the positivity of the higher derivative coefficient to weak gravity conjecture. So there was some attempt by Gary Hsu and the collaborator last year, and they, as far as I know, I can see it doesn't quite match up. There are some inequalities that is needed for the kind of things that Rubosch, Motor, and the collaborator did. And then, but the inequality that come from the causality unitarities, not quite that. But you were saying that there are some way that they are related. Could you expand on this a little bit and explain more detail in terms of equations, how this, what was were you referring to?
So this is one way of talking about the weak gravity conjecture. If we just have one charge here, just a single U1, so I don't talk about anything else, then even in the real world, electromagnetism in the real world, you imagine making this plot as a function of charge. Look at the object of smallest mass with that charge, and just plot it. Is there an object at any given charge with some mass? So for example, with charge 1, there's the electron. Okay, no problem. So I'm going to measure this mass-to-charge ratio in Planck units. So here is 1, where 1 is actually defined to be what you get from an extremal black hole at enormous charge. Okay, so when you're at absolutely enormous charge, there are extremal black holes. So out here we have extremal black holes. And down here in the real world, with this ratio of some incredibly minuscule number of order m electron over m Planck, we have the electron. Okay, so we have the electron out here. We have extremal black holes up here that are sort of in the GR approximation, the two derivative approximation, they're just exactly on this line. Right? And so I think there's a generally nice question, what does this curve look like? You have to be slightly careful because, of course, you could have objects in between that are not actually stable. Okay? Even the whole point, in a sense, of the weak gravity conjecture is that none of these things should be stable and should be able to, or one of the initial motivations, they should be able to decay down to the lightest sky. But nonetheless, let's be a little less anal for the moment. If they're really super long-lived, let's not worry about it. Okay? Certainly these extremal black holes are very, very long-lived. It's ultimately Schwinger pair production, which is making them decay, for example, or Hawking radiation, which for extremal black holes is more or less the same thing. Okay, so what does this curve look like? And as Hirosi was also saying in his talk, one way that it could look that would be totally compatible with the weak gravity conjecture and would imply many other things, that it just goes down, that you sort of approach this line, that you approach it from below. I want to bring this up because this is part of it might be superficial, but what I see is a commonality between some interesting positivity statements across many different subfields right now. We have fascinating positivity statements in quantum information theory going back to the monotonicity of relative entropy. We have many of their gravitational analogs, the kind of things Raphael was talking about, things that we've, on the one hand. We have the positivity of higher dimension operators that I was talking about. We have things like the weak gravity conjecture, which also involve inequalities of this sort. But it's not just that they involve things that are greater than 0. In many cases, you have strengthenings of these statements. Instead of things just being positive, you go to having a curve where things are monotonic. Okay? So instead of just relative entropy being positive, it's monotonic under coarse grading. Instead of having, anyway, so we have extensions of positivity statements, a kind of convexity statements. And so that's sort of what I imagine is going on here, is that instead of just saying the purest version of the weak gravity conjecture, there must exist somebody down here somewhere, which is a very weak form, which also can be pretty useless if the guy that's saturating is all the way up here. It would be more interesting and a much more detailed statement if it said this curve always goes down, except in supersymmetric theories where the U1s are BPS, where it's exactly a straight line. Okay? So
that was a question, and
yes.
But you are sort of suggesting that this has to do with unitarity.
That's right, exactly. So now, that's right. I'm sorry. So that's what I said. I was just unpackaging your question a little bit. So now let's talk about let's talk about what could be going on. So first of all, for example, Hirosi explained that if you take the spectrum of non-BPS charged states in the heterotic string, for example, from that beautiful formula with the p left squared and the p right squared, it exactly looks like this, right? It approaches a line from below, and for the things that are not protected by supersymmetry, there's the extra negative contribution from the tachyonic part, which is exactly pushing it down. Okay, so that's an example in any perturbative string theory that the spectrum indeed looks like this. Okay, so that's one example. But of course, if that ends up being true, and I don't know if it's true, but if it ends up being true, you need to find an explanation for why it's being pushed down kind of everywhere along this curve. Okay, and that explanation can look different in different parts of the curve. So, what Lubos and friends did a long time ago is just add higher derivative operators. So in Einstein, in two derivative approximation, the mass-to-charge ratio is 1. And as I said, we have root g r and f squared in the action very schematically. So we know that in the extremal black hole solution, r and f squared are comparable to each other in the extremal black hole solution. And therefore, that tells you what the higher dimension operators are that will matter at comparable order to each other. Okay? R and f squared are about as big as each other, so the higher dimension operators that will matter are r squared, r f squared, and f to the 4th. Schematically. Okay, so these are the kinds of higher dimension operators that can affect the mass-to-charge ratio. And so what you can do is put them in with any coefficients, just compute what they do to the mass-to-charge ratio. Okay, and that's what these guys did a long time ago. So you get a formula for the shift in the mass-to-charge ratio that's a function of the sum of the coefficients of these guys weighted with M Planck in various ways. And therefore, you're making a prediction that that funny sum, weighted sum, should always have a uniform sign. Okay. Now you can ask, do we know anything about that weighted sum from other arguments? Like, okay, that's right. That was Hiroshi's question. So, and what we already did in our very first paper with Cameron on the weak gravity conjecture is talk about what happens, let's say, if you only have that guy. This is kind of defensible, right? Because if you have some light charged particles or something, they would only produce this radiatively. And so this is, it's reasonable to ask what you get just from one of these guys. And this is an interesting case because these are also exactly the operators that we can bound without gravity just from the superluminality constraints. And what I was mentioning is that when you put in the correct signs that guarantee that it's not the standard unitarity superluminality signs are also the ones that push the mass-to-charge ratio down. Okay?
So I understand. So with additional assumption that only f to the fourth is generated, then the unitarity constraint push things down.
This is already the statement from 2006. Now I'm going to say something new. Okay? Okay. So now, why is it challenging to say more? Why is it challenging to say more? Well, and there's something kind of interesting here. These operators, while they're all equally important for the shift in the mass-to-charge ratio, have a rather different status when it comes to what they do to scattering amplitudes. For example, this operator directly gives you a 4-photon scattering amplitude. Very good. And that's exactly the kind of stuff that we're talking about. So you'd expect there's unitarity bound on it. What is this guy doing? This guy only gives you a new kind of 3-particle amplitude. Okay? This only gives you a new kind of the wrong helicity, the like plus normal scattering amplitudes involving gravitons, or like for a photon, graviton would be photon plus photon minus graviton. That's the usual GR 3-point function. This 3-point function gives you a plus guy. Okay, so interesting. So there is some funny plus graviton 3-point function, but a priori from unitarity, there is no reason either way to sort of care about it. In fact, the whole obvious unitarity program is about consistency. You give me the 3-point functions, and then the 4-point functions should be compatible with it. And you know, in R squared is different still. In fact, let's just stare at this guy for a second. In 4 dimensions, it isn't even there, right? And yet people talk about the R squared term. You know, what are people talking about when they talk about the R squared term in string compactifications if you're compactifying to 4 dimensions? Well, secretly, there's a dilaton sitting there. Okay? And so they're really talking about this dilaton-graviton squared coupling, again of the wrong helicity. Okay? So the wrong 3-point function, the wrong helicity 3-point function involving gravitons and the dilaton. But that's why it's kind of interesting that it's this funny linear combination of these guys that affect the mass-to-charge ratio, but they have a different status from the point of view of sort of standard unitarity argument. So what various people are doing, and I haven't studied the papers in detail, are making, I think, pretty stringent assumptions about what they're integrating out. They imagine they're coupled to some particle at tree level and so on. That's right. And then they try to say something, which you have to do for the reason I told you, because otherwise, flat out, this is not, you can't directly apply these, the 4-point unitarity argument for this reason. So let me then finally say the statement I was making at the very end quickly, okay? So let's go back to this picture. Like somewhere far away here, you imagine for black holes, so let's say we're really thinking in the context of string theory, even with a weak coupling. So the weak coupling, let me make this as a function of mass. Okay? With a weak coupling, here is M string, here is M Planck. Okay? And so very, very loosely speaking, down here is what we would normally call, you know, elementary particles. Here is what we'd normally call string excitations. They're still elementary particles, but there's lots of them, so it's very stringy. And here is what we'd call black holes. Okay? Even though, of course, though that's the rough categorization. And so what happens, and actually there's this higher energy scale that I won't write the general dependence of, but there's a higher energy scale here above M Planck where the black holes become bigger than M string inverse. Okay? Okay, so you have to go right at the Planck scale, the black holes of a size M Planck, but you know, you have to wait to go to even bigger masses where the Schwarzschild radius gets bigger than the string length. So in string theory, really, there's both this lower energy scale where you start seeing strings, and then you got to go well parametrically past M Planck before you really see semi-classical black holes.
So you mean M Planck square divided by M string?
In 4 dimensions, that's what it would be. But as a general, there's a d minus 3 over d minus, anyway, there's that kind of power in general. But yes, something of order M Planck to a power over M string to a power. So said a little more in detail, in this regime it's string excitations, or you could call, in this regime, the whole thing you could call string balls. And out here would really be black holes. Okay? So anyway, so you could go out in this regime and use the higher dimension operators you get from string compactifications to calculate the shift in the mass to charge ratio. That's the exercise. That's the exercise that was done, and in every known compactification, you get the right sign. Okay. Now, what I was saying is something else. Is that there's another scale way the hell out here of order e to the m Planck squared over m string squared times m Planck or m string, but it doesn't much matter. Okay. There's an incredibly long, in fact, sorry, it might even be to the fourth. Don't quote me on this power, okay? But I'll explain where it comes from in a moment. Yes, I think it's to the fourth. Okay, so where does this come from? Well, and this is related to my constant caveats about ignoring the running of couplings in the, of the higher dimension operators in the low energy theory. You see, let's say we talk about the f to the fourth coupling. So how is it that you practically get the f to the fourth coupling in string theory? You take some tree level amplitude, you look for the piece that looks like the appropriate power of s at low energies, and you extract the coefficient of f to the fourth. So there's some kind of f to the fourth that's suppressed by power of the string scale. Okay? But there's also a loop correction in the low energy theory with gravitons and photons. This is one diagram. There are many diagrams. There's a loop correction that just by power counting has 4 powers of 1 over m Planck. Okay, so there's a 1 over m Planck to the fourth. So it has exactly the right units to give you f to the fourth, but it has a log in it, like everything does. Okay, so this is the log running. So this goes like log of the energy scale, log of m string over the low energy scale. Okay? Now, precisely because of the weak string coupling, this piece totally dominates over that piece for an enormous range of energies. That's why we basically are ignoring the running of the coupling as you go to low energies, because it's vastly subdominant compared to the leading piece that's sitting there, until you go to super duper exponentially super low energies where the log finally wins. Okay? So that's guaranteed to happen eventually. So in other words, there is a regime, even when the string scale, of course if all the scales are on top of each other, let's say all the scales are on top of each other, then the notion of higher dimension operator coming from integrating out quantum gravity is totally ill-defined, because the low energy couplings are just dominated by the running in the low energy theory from calculable gravity loops. Okay? If you have a weak coupling, so the string scale is beneath the Planck scale, then the notion of higher dimension operator is perfectly well defined. These are the objects that we obsessed for 4 hours about calculating and saying positivity about in my talks. But if you wait long enough, you go to exponentially low energies of order e to the m Planck to the fourth over m string to the fourth, okay? Then they will still be dominated by the calculable pieces at long distances. And so now we can ask the question in a completely model-independent way, because it's dominated by gravity loops, calculable gravity loops. What do you get from them? Okay? And so now I'm talking about way out here, way the hell out here, what is the sign of this correction? This is calculable because we can compute the beta functions. Okay? We can compute these logarithmic corrections, and that's the result that I mentioned. That,
How about
yeah.
r times s squared?
So that's a cool thing. We did the calculation only in 4 dimensions. In 4 dimensions, 2 things happen. R squared is irrelevant. It's a total derivative. It doesn't affect anything. RF squared does not run at 1 loop. That's a very nice fact, okay? And this is something many people have observed. People observe these mysterious zeros in the running of higher dimension operators in the context of the standard model effective field theory. If you look at all the dimension 6 operators in the standard model involving the Higgs particle, there's some 57 by 57 anomalous dimension matrix that various phenomenologists murdered each other to take credit over for the five years ago. But people also observe lots of mysterious zeros in this anomalous dimension matrix. So examples of things that did not run despite the fact there's no symmetry stopping them. Okay?
Stringy correction
Yes.
still gives the r times s.
That's right. Stringy corrections, that's right.
So there
Yeah.
can be competition between r times f squared and f.
That's right. But again, if you wait long, for then you'd have to wait even longer for those things to adopt. But eventually this thing will dominate over everything. Okay?
Okay, well,
Yeah.
thank you
Yeah.
very much.
Yeah.
That explains.
Yeah. Yeah, and I should say that the reason for the absence of the running of RF squared is a special case of a general thing that Cliff Chung finally explained. Cliff gave a beautiful explanation for the absence for these zeros and all these things. And it's in fact it's a counterexample. It's not a counterexample that this lore that everything is generated by symmetries is false. The really true fact is all processes that are allowed as cuts should occur. And we very well know, for simple helicity reasons, all kinds of things are forbidden at tree level. All sorts of amplitudes are forbidden at tree level. So the reason why the RF squared doesn't run at one loop is that it would show up as a correction to a 3 plus and 1 minus amplitude involving photons and gravitons. And there are no cuts that can contribute to that because of the structure of the tree amplitude.
Very interesting. So this is a very universal fact.
That's right. This is a universal quantum gravity calculation. Right? You can, people like Donahue have stressed, I mean, just like in the Cairo-Lagrangian 30 years ago, there are universal things that you can make about the logs. It's just they're a little boring. I mean, they don't...
Isn't that a bit disappointing? Because you are explaining weak gravity conjecture in purely low energy terms.
Well, you see...
So it's not a Swampland. So I should exclude weak gravity conjecture from Swampland.
Well, so you see, this is why it depends if you think that what you're supposed to try to do is just say there's one stinking guy down here, or if you're trying to understand this shape of a curve like this. If the shape of a curve like this I think is actually more interesting, because there's some reason why this is happening, and the name for that reason sort of depends on energy scale. But yeah, unlike many of my friends, string theorists don't talk about disappointment. It's the people who care about the LHC who use the word disappointment. But anyway, unlike many of my incredibly narcissistic theory friends, I don't use the word disappointment when it comes to anything to do with physics. Physics is physics.
Learning something new is always...
Yeah, right.
Thank you.
Thank you. Sorry.
Okay, now I want dumb questions from students. Please.
I have a question for Professor Oguri. The conjecture about non-SUSY ADS means that DSCFT is applicable only to supersymmetric theories. Namely, if ADS non-supersymmetric does not exist, this is restrictive for the correspondence.
Well, indeed. I mean, so that's why our conjecture is a little bit bold. We are saying that the DSCFT correspondence works only for supersymmetric situation. Of course, there are non-supersymmetric conformal field theory. So that means that so it's something that conformal bootstrap people can try to test, which is that so this conjecture, the other side of the conjecture is that there cannot be non-supersymmetric conformal field theory which can have weakly coupled gravity dual. Now, there are some expectations that if you have a conformal field theory with large gap, then they have a reasonable gravitational dual. Because if you have a gravitational dual, then you have a supergravity multiplate, and then there is a large gap until you get to the string theory threshold. And so in the large n limit, this is a large gap. So one can ask, could a conformal bootstrap either show that this is indeed the case, that if you have non-supersymmetric setup, you cannot have this gap, or can you construct an example of such conformal field theory? Well, what does large mean? Yeah, well, yes, that's a good question. But when you have, when you say that you say that there is DSCFT correspondence with weakly coupled gravitational dual, you always assume there is a large number, and that with respect to that large number, so that means so when you say that there is you claim that there is a weakly coupled gravitational dual, say in the non-supersymmetric theory. That you should mean that the conformal field theory comes with that parameter n, and then the gap scales like some power of n. That's what I mean.
So you're imagining not one theory but a whole.
Sure. Yeah, because otherwise DSCFT doesn't mean much, at least in the current technology, because we don't know what the gravity dual means. And my argument with Qumran is assuming that. Not only you have, for example, you don't consider the situation where you can have ADS, non-supersymmetric ADS, which is strongly coupled, which has strongly coupled gravitation. Because then we cannot exclude, because our argument is based on the semi-classical gravitational picture.
But I just meant, if you have something where it's 20 times bigger, I don't know, the gap is a factor of 5, 10.
Yeah, we are only considering the case when you can have parametric control. So
between the eigenmodel, so there's some special C or gap or something at which you claim that nothing should happen. There's a number out there.
well, we are making a asymptotic statement. It could be that there can be non-supersymmetric ADS, which has in which the ratio of ADS radius and Planck length can be like 10 to the 100 or something, but just one example, and I cannot exclude such a theory.
Also related to this question, what about the examples that we know of, like for when we turn on temperature in the CFT side, which breaks supersymmetry? Does that also exclude?
No.
Okay.
No. So because it's one of the states in the supersymmetric theory.
I would like to know how the story ends with CPT at the beginning of your.
Yeah, very good.
Because
I still owe answer to that question. I think that so I haven't explained first of all how you exclude parity, for example. So to begin with, so this is a question of just to remind you, this is a question of absence of global symmetry. And so in my lecture, I only explained internal global symmetry, which commute with space-time symmetry. But you can consider, for example, parity as an example. And the reason it works is that you can consider the space Cauchy slice so that it is parity invariant. And then you can also arrange, when we make this argument, when we made this argument when we divide the boundary into segment and we do this, we can set up this entanglement wedge, the series of entanglement wedge, so that it's also parity invariant. So then the parity transformation should preserve this configuration, and then we can ask, well, that parity, can there be local operator in the bulk which transform non-trivially under that parity transformation? And then that would, if there is, then it's contradict with this kind of thing. And I think that's a very interesting statement, because when we have quantum theory of gravity, you can ask, should I sum over all possible topology, or because if you have quantum theory of gravity, you are supposed to sum over all geometry, so you'd expect to sum over topologies. But should we add sum over all topology? For example, should I sum over non-orientable geometry or not? And if you have a parity as the exact symmetry of quantum gravity, then you have a choice of not summing over non-orientable manifold. But since parity is not an exact symmetry, so you will be compelled to sum over both orientable and non-orientable geometries. Now, this is not the case in two-dimensional gravity, because there are examples. So, for example, type 2b string worldsheet is an example of two-dimensional gravity, and there you are only supposed to sum over orientable surfaces, right? So there are examples in a heterotic string also. So there are examples in string theory where parity is an exact symmetry. Okay, and then so that was one of the things I was saying. So now the parity is preserved. The time reversal can also be argued in this way if I choose a Cauchy surface exactly, and charge conjugation is also an exact symmetry. So so you can have that symmetry. Now, how about CPT? So CPT should be an exact symmetry. So that means that the combination of each one of them is cannot be an exact symmetry in this way. But the combination of this should can act non-trivially. So I think what happens is that so you can have CPT, and CPT can act non-trivially. Well, CPT theorem says that it's always an exact symmetry of the conformal field theory and so the quantum field theory, but it doesn't mean that it's exact identity. So that means that there must be an operator which transforms non-trivially, right? So the question is that so how this is avoiding this problem? So that was the question. So I'm trying to answer this. Yeah. Yeah. I still haven't done the exercise. I think I have an answer, but let me try to let me add the note to this to my lecture note, and then.
Because if CPT is not an allowed symmetry...
No, CPT is the answer is that CPT is an exact answer.
Okay, yes, yeah. Because the contrary would be that we have the broken of Lorentz invariant.
Yeah, so let me try to recall. Yeah, so I cannot do it in real time, but yeah.
Okay, so I have a question about this non-SUSY ADS.
Yes.
So people recently were talking about this SYK models, and
this is one-dimensional.
Yeah. So what makes
so
it
yeah.
different?
So the thing is that so I said this at the beginning, but so I can exclude non-supersymmetric ADS in a case when the gravity the bulk theory is Einstein gravity coupled to finite number of matter fields. And SYK is not an example of this because bulk theory is not Einstein gravity but Jacques-Teitel-Bohm theory. And there are lots of funny excitations also. The other issue is that theory has no separation of gap. So there are stringy. So it was shown by I think Stanford and Maldacena that these are not weakly coupled gravitational system. But there are stringy-like excitation in the spectrum, which is not parametrically sort of massive. So this is not a counterexample.
Now a question to both Nima and Hiroshi. You were talking about now the weak gravity conjecture and about how with this kind of low energy effective theory arguments we can actually get some motivation for the weak gravity conjecture. How does this kind of arguments relate to weak cosmic censorship in the connection that appears to exist between weak cosmic censorship and weak gravity conjecture?
So this is a very interesting development. So earlier there was so you're referring to the work by Jose Santos and also with Gary Horowitz. And so the earlier they had some counterexample to cosmic censorship hypothesis. But then they realized, I think Qumran pointed out, that if you assume weak gravity conjecture, then the kind of theory that they are considering is not allowed. So it seems like cosmic censorship is protected by weak gravity conjecture. I do not know why, and in fact, from the point of view of string theory, a priori, there is no reason that the cosmic censorship should hold, because even if there is a naked singularity, string theory can resolve it in a nice situation. And there are many examples of string theoretical states, like some branes, typically even D branes in some different particular dimension can have naked singularity. And so I do not expect it's a general feature. It's a very curious fact that in certain situations, cosmic censorship is restored with weak gravity bound, but I'm not sure what kind of lesson one is supposed to learn from interesting observation. But maybe Nima can have something.
Make a little comment. I don't have anything much more to say than that, but I just want to make two comments. One about cosmic censorship, period. So along the lines of what Hirosi was saying, there's one sense in which if cosmic censorship was violated in an interesting way, it would be, well, this has been emphasized to me by Ed Witten many, many times, that there's various things that people mean by violations of cosmic censorship. There's a lame kind of violation of cosmic censorship, which is that the equations develop a singularity somewhere that you can see, but just the same way as if you look at water coming out of a tap, you know, and it gets narrower and narrower as you come down by the parabolic shape, and somewhere at the bottom it pinches off, and so, okay, something is happening now, there's some kind of singularity, but it doesn't do anything for you. It's not exciting. It's not, and something is happening. You can repair it by some simple boundary condition and continue. Okay, so there's that kind of very formal mathematical breakdown of cosmic censorship, and there is the exciting breakdown, which is if you have a naked, I mean, what I would naively think, you know, without knowing anything. I'm a dumb guy. You can have like a naked singularity sitting there. That means that you can get a Planck scale accelerator for free, right? You just sit out here, you throw your garbage into the naked singularity, poof, all sorts of Planckian wonderful stuff comes out, and the particles that come out of this process probe all that Planckian stuff that went in at the singularity, right? That would be amazing. If those things existed, then we could sit from far away, throw things in, and probe very high energy physics from low energy experiments. That's the sort of thing that would somehow violate the spirit of decoupling, right? This idea that you cannot cheaply learn about high energy physics from low energy experiments would be messed up if you had useful cosmic censorship violating naked singularities in that way. Having said that, I simply don't know enough about the kind of singularities Gary and Santos and others were talking about to know if they were the useful or the useless kinds. But if they were the useful kinds, then they might be related. Somehow it's a way of this kind of UVIR decoupling of being protected somehow. So that was the
in
comment.
the case,
yeah.
In the original example they found, they had gauge field that that became infinite in an infinite volume near the boundary. So I think it would be the useful.
It would be useful kind. Okay, good. Then in that case, there might be some moral reason for it.
You're saying that even in string theory, cosmic censorship can maybe require to hold.
If you somehow, yeah, that's right. If you think, exactly, yeah. I think there's some principle of justice in physics that you have to build colliders to learn about high energies, right? That's and if this kind of cosmic censorship was violated, if the useful kind of cosmic censorship was, the useful kind of naked singularity was possible, then you wouldn't have to do that, so and that would be, yeah, that's right. There should be a no free lunch there. Yeah, that's. And I want to make one other small comment that. Often in some of these discussions about the weak gravity conjecture, it seems a little stupid because you say, here's a theory that doesn't satisfy weak gravity. Hey, I'm going to just add a light scalar, light charged particle, poof, now it all of a sudden does, right? No, it's fine. I mean, it's a constraint on effective field theory, but it seems easy to fix up. And it's also what these guys are doing, right? They say, if there's a light charged particle, then it affects this loop. Perfectly fine. I just want to say for anyone who's thought about this knows this, but people who haven't, the real version, the version of the weak gravity conjecture that has real teeth when you have weak coupling, so you have a weakly coupled U1, is the magnetic version. The statement, the statement that there should exist a magnetic monopole with mass-to-charge ratio smaller than 1 is a much more interesting statement, because that's really what tells you about a low-energy cutoff. I mean, the sense of the weak gravity conjecture was not just that some random old particle should be lighter than Gm Planck, but some kind of cutoff should be smaller than G times M Planck. And then all of the difficulty of this project was figuring out what the hell we should mean by the word cutoff, because it's a loose notion. But if you have a U1 gauge field and you have monopoles, the mass of the monopole is a good measure of what you mean by cutoff. And in all examples that we know of, on the lattice, in gut models, and so on, the inverse mass of the monopole is indeed the scale at which the U1 description of the theory changes and has to be replaced by something else. So it's a magnetic version of the weak gravity conjecture that has sort of more content. It tells you something about some kind of low cutoff compared to the Planck scale. And one way of motivating it is if you ask for the lightest monopole to not be a black hole, then that tells you that the cutoff has got to be smaller than g times m Planck, where by the cutoff you mean the mass that you would get just from the magnetic field surrounding the magnetic monopole cut off at some size. Okay, so anyway, those are the two quick comments.
So I have a question for Tom. So when you were talking about UV finite quantities, you talked about differences of entanglement entropies in two different states. And you said that works sometimes. Can you elaborate a little bit on that? Like, what are examples where it doesn't work?
Let me remind myself. You can have, basically it's a question of whether you can have state-dependent divergences. So divergences that depend on the actual state. And it turns out that, yeah, there are some divergences that you can motivate, which sort of depend, it depends on dimensions of operators and such, but depend on the expectation value of some operator times epsilon to some power. And these can arise in ADSC. You can see these in DSCFT by computing entanglement entropies in various states. You have to do a little bit more work, but these can be there. And then, so then it won't decouple. So there's a row here, and then when you calculate delta S, this will not be finite. However, it's always true that in all of these cases, and there was a paper by Aaron Hall and Don Mouth that discussed this, and they found that all of these cases, something like this, the relative entropy, the relative entropy which contains the change minus the change in the entropy plus the change in this expectation value of the modular Hamiltonian, this is always finite, so it's not affected. So this is there and there, and they cancel.
But there's no pure CFT or pure field theory version of this argument?
Yeah, I think they have field theory versions of it too.
Oh, they have a field theory version of it too. It's not just.
DSCFT and field theory. Yeah.
So maybe I should make one comment about CPT. So it's just slightly defined, but one comment is that the way that you prove CPT compatibility theory is that if you combine CPT, then essentially it's actually part of the location, which is actually connected component. So P and T are not connected components of the Lorentz group, but group. But if you consider CPT combination, it's actually related to the connected component. And that transformation to be regarded as actually non-normalizable part of the bulk detail moments. And so that's not excluded from this argument. So I think that along this line can explain why P and T are separately not allowed as an exact symmetry, but CPT can. But I can try to refine it.
More questions? David is also here, remember? You want to ask him?
So a quick question for Oguri-san. So you have given an argument for why the no global symmetry should hold if, in the holographic context. Would you be able to put some other conjectures into the holographic setup as well? For example, distance conjecture?
Yeah, so of course we don't have a proof. So for other conjecture we don't have proof, but there can be a possible way to generalize this, and that it will be interesting. So for example, one idea that can be relevant in this context is that, so I mentioned the connection between our proof that there is no exact symmetry. And the theorem in quantum information theory called Easton-Knell theorem, which has to do with how the quantum error correction requires that unitary operator acting on each individual Hilbert space cannot act non-trivially on code subspace. Now, there is actually some refined version of Easton-Knell theorem, which quantify how this symmetry can be broken, that all code subspace can be approximately protected. So there is some kind of refined version of this kind of theorem in quantum information theory. So if properly understood, maybe that can lead to refinement such as weak gravity conjecture that shows that, basically weak gravity conjecture says that you can, one way to think about weak gravity conjecture is that there is a lower bound. So if you take gauge field coupled to charge the particle, if you take the limit when the gauge coupling goes to 0, then it becomes global symmetry. So weak gravity conjecture says that there is a lower bound of how much you can make the gauge coupling small. Right? So in that sense, it's a refinement of no global symmetry conjecture. But maybe those are related to some refinement of Easton-Knell theorem, for example, in quantum information theory. So there can be a way to, but of course, if I know how to do it, I'll be writing papers on this. So obviously this has not been done. But there could be a way to get this connected.
Also, yeah, and also a couple of days ago you said you could extend this ADS to Minkowski as well by taking...
No, I cannot. I was suggesting that there can be a way of showing this by taking appropriate limit of radius of ADS to go to infinity, but this has not been done. This may be yet another way to extend what we did. And it's interesting, this has not been done. Well, naively, you may imagine that just take the limit of it, but there are various technical issues associated to it. Nima had some comment.
A question also, well, two different questions and comments on, first on the distance. So you were talking about the sort of mathematical distance on modular space, right?
Mathematical, but in the sense that the distance is measured with respect to metric in the kinetic term.
So there's some intrinsic metric given on the space of scalar field, and you're measuring it via distance in that envelope. There's a related question people have talked about to try to make sense of this idea of whether trans-Planckian traversals are good, bad, what they
Right.
are, which is whether there's any dynamical process, whether you can kick a scalar field and actually watch it traverse an amount bigger than m Planck or not, just as a dynamical process. And certainly if you try to do this in flat space, or you try to do it in lots of sort of simple ways, what you find over and over again is that every time the traversal starts getting larger than Planck, where the traversal happens is hidden behind the horizon.
Yes.
But that's only been seen in various toy examples,
Mm-hmm.
and so on. So my first question is, do you think there's any relationship between this cleaner statement about the cleaner mathematical statement about distance on moduli space and any statement of this dynamical nature, whether any observer can actually see the trans-Planckian traversal take place or not?
Yeah. So indeed, you are quite right. I think I first heard the argument from you, but that if you try to sort of move the scalar field wave for distance greater than Planck scale, then that requires some kinetic energy, and then that can automatically generate a horizon. So I think Zohar also has a version of this argument. And so therefore, that argument, however, is of different consequence. Here, we are saying that if the scalar field traverse for longer distance, then low energy effective theory changes. Whereas this argument shows that even if it did, you won't be able to see that. So these two regions are not in the sort of same causal patch, right? So these are sort of slightly different nature.
Although the reason I brought it up is that this logarithm that
Yes.
you have, right? So it's not that logarithm shows up also all over the place in this. For example, we try to take a cosmology driven by the kinetic energy of a scalar field.
just as it seems to show up in the actual distance among
Right. Yeah. I'm very intrigued, always intrigued by this idea, but I have not been able to sort of find the proper connection. There ought to be one. You had also some comment, you said.
A second general statement about this business about whether about the relation between supersymmetry, ADS, that kind of
Right.
There was something of this flavor that people like Tom Banks talked about for many, many years, which first came up in the context of matrix theory, which is where after all, the sort of emergence of flat space in matrix theory is associated with the moduli space of the matrix quantum mechanics. Right? And if you attempted to make a non-supersymmetric version, the whole space-time collapsed. Right? So there, the conjecture was that it should be impossible to find in a theory of quantum gravity flat space, exactly flat space, unless it's supersymmetric. And I'm wondering if there is a relationship between that conjecture and yours.
There might be one, yes. Can you reconstruct Tom's argument?
No, I mean, it was just, no, I can't reconstruct it. I think it was based on this experience with what goes wrong when you try to brutally break supersymmetry.
Okay, yes.
But what I wanted to say is that there's at least a concrete avatar of this. I think there are many questions in this neighborhood that might be amenable to some field theoretic attack. For example, a question like this is closely related to another one. Can you find a non-supersymmetric field theory with exactly flat directions? Period. I think it's a very, very beautiful question. Naively, no. You would say, well, I have to fine-tune the Coleman-Weinberg potential at one loop, and then I'm screwed at two loops, or something like
Right.
that. And that's exactly what you would say if someone handed you a supersymmetric theory and your name was not Wessers-Amino. Right? So you would not.
But what's the logical connection of this to gravitational statement?
It's in the same flavor. After all, in the place that it came up in the context of matrix models, you're trying to preserve exactly flat directions.
Okay, I see. So I see. So Tom's argument was that suppose you have matrix theory, for example, but then if you break supersymmetry, the potential generated, so you cannot have a asymptotic infinite space. I see. So that's a kind of argument.
It seems like another question of the same flavor, the sort of thing you're talking about, but then there's cousins of it that sound like interesting field theory statements that you might be able to prove this.
Right. Yeah. Okay. Good. Yeah. Thank you.
Can I ask Hiroshi Oguri something? So I didn't attend all your lectures, sorry, so maybe you already commented during the lectures. Do you have anything to say about this DSCFT by Aninos, Hartman, and Strominger, the dual to Vasiliev gravity in the Sitter space?
I do not. But one thing I can say is that at least for my talk today, the only kind of theory that I was excluding are the theory which has low energy Einstein gravity coupled to finite number of matter field description. And the Vasiliev theory is certainly not included in this example because there's infinitely many massless degrees of freedom, for example. And so certainly this is not so first of all, it's very interesting they can construct a digital space in this way, but it's not the class of theory that can be excluded by our argument or conjecture.
Can I make a small comment about the sitter? It's a qualitative, simple qualitative. Actually, you know this point, but I just want to make the comment. I think it's very simple, but sort of fascinating point. That there's many qualitative differences between DS and ADS. But as far as something like DSCFT, some kind of stringy picture for what the sitter might be, there's the following qualitative problem. In ADS, we have this picture, let's say in ADS 5 cross S5. We tune down the TUF coupling. We tune the TUF coupling up, we get these string excitations that go up. We turn the TUF coupling down, and a little bit the CFT becomes free. All of these stringy excitations come down and eventually become massless. Question, is anything like this possible in the sitter space? Could you imagine some limit where you tune down a whole bunch of stringy-like towers? After all, we expect they're there in the ultraviolet, even in de Sitter space. Is there some limit you can imagine tuning down so they all come down, become very light, massless even, and then you turn some parameter back on and they start becoming heavy? That is impossible in de Sitter.
Oh.
Massless particles, but nothing in between that's got to jump to something of order Hubble.
Oh, that's very interesting because.
What's going on with string theory of de Sitter space? It cannot look like some parameter. You gradually dial down, the strings come down, and become lighter. And so that's a qualitative difference.
So does this apply also to accelerating universe, or is this strictly digital?
No, it implies. I mean, it's for all practical purposes, an accelerating universe that's accelerating long enough looks like de Sitter.
Okay, very interesting, because then it is very much similar to the kind of argument that Qumran and I gave with Gary Hsu and Elan Party, because we took an issue that if you have such geometry, and then but in the asymptotic regime, then you have a tower of light particle coming down. And then we gave some issue with this kind of situation because of this entropic argument. But you are suggesting that there are alternative ways that this can be problematic by unitarity.
If they have spin bigger than 2, yeah. If they have spin bigger than 2, particles with high spin bigger than 2, but look like string excitations are excluded in this intermediate window.
Oh, so I didn't know that. Is this who did this?
Oh, this is just unitarity in de Sitter space.
Oh, okay. So you just know this as a fact. Sorry?
Yeah, sorry, I forget the names of everything. It's the Gucci.
Oh, okay. Thank you.
Yeah, just very, very related to what you were saying just now. From what I've heard of DSCFT, I think it is known that the CFT would have to be non-unitary. Would that be related to what you're saying?
No, what I'm talking about is not a formalism-dependent statement. It's a statement of what the bulk looks like. I'm just saying there's no consistent set of, no decent set of theories that you want to call decent. But have the property of there's a parameter that you dial where, in one regime it kind of looks like normal particle physics, and then strings at very high energies living in de Sitter space, and as you dial it down, all those states come down and become arbitrarily loud. They have to get switched up, something bad has to happen to them around Hubble. You can't have them come back there. So it will look qualitatively different than what we expect from CFT.
Very interesting. Raphael had a comment. I'm not a chair. So
Yeah, I have a question for Tom. You introduced this monotonicity of relative entropy in terms of quantum channels. Do you know how one can think of these quantum channels or these so-called recovery maps in terms of path integral formulation? Yeah, in terms of, yeah, exactly. Yeah, but and what's the consequence of this thing for holography? I mean, if we have some sort of, as you know, these strengthened versions of monotonicity or relative entropy, then if we translate this to holography, maybe, yeah, let's follow up, yeah.
So, I mean, formulating that away from the tensor network context in quantum field theory, I think is interesting to try to do. But I don't know how to do it.
Can I also ask you a question? I also would like to ask you a question.
Okay.
So you emphasized several times that in quantum field theory you cannot factorize a Hilbert space, and so you can define algebraically relative entropy. And if you want to define something like entanglement, you have to drill a hole and then to put some boundary conditions. So what is the status of trying to define entanglement entropy in QFT, and what kind of boundary conditions people try, and how things depend on them? You know, what's...
Well, there's various ways to...
Yeah. Any other questions?
I had a question for Professor Oguri. In the de Sitter-Swampland conjecture, you showed these two inequalities in the morning, and there was this constant C prime in the inequality with the second derivative. And I wanted you to recall or explain why this C prime should be of order 1. What is the argument for this?
Well, so the condition, so I didn't specify, but in fact there is a precise value to C prime, because the condition comes from the requirement that you shouldn't have two sort of large negative eigenvalue for Hessian for the potential. Because if you have, then the quantum fluctuation becomes unstable. So in de Sitter space, you have a horizon. So accelerating universe, you have an apparent horizon. And then if the wave exit the horizon, then it becomes classical. And then so if you have negative, so if there is a negative direction for Hessian, there is an instability mode. And then, but if it exits the horizon, then it becomes classical instability. So so you do not, if that happens, then semi-classical approximation breaks down. So there is a specific number that you can put for the lower bound for Hessian, and so that's that number.
Where can I find this number? I mean,
well, I think in any sort of literature on the standard cosmology literature describe this.
You're talking about eta. Eta's got to be bigger than 2. Is that the number you're talking about?
I think it's eta. It's related to eta, I think. Yes.
Any other question? Still there is, we have still a few minutes.
I have one for Nima. You mentioned this generalized unitarity where the branch code arises from, here, down here. No, right here. So can you expand a little bit of that generalized unitarity and where does it come from, or if you can understand it from something in string theory or something like that?